This is Mr. Lee. In this video, we're going to go over Gauss's laws, but for a insulating sphere. All right, let's begin. So to start off, I want to go over the way we can solve for Gauss's law outside of a insulating sphere. So if we have a sphere here, and let's say this sphere has a total charge. So here's our insulating sphere. So the important thing about this insulating sphere is that the charge is spread within. Okay, it's spread within, and usually we just say it's even unless told otherwise. So we're about to use Gauss's law for outside the sphere. Okay, and so we have Gauss's law formula. We have the surface integral of the E field dot dA is equal to Q enclosed over epsilon naught. Okay, so from this formula, it's really important for us to be able to narrate what's happening with this formula as we're using Gauss's law. Only because Gauss's law is a tool that we use, and so being able to know how the formula fits within the tool really does help. So if we take a look at this formula here, right, and we're taking a look at the outside. So if I were to draw the Gaussian surface, let me just draw the sphere over here, and let's take a look at the Gaussian surface out here. Okay, so this is my Gaussian surface. Um, we can say that the E field, which is what we're trying to find, we can rearrange the formula so it looks like this. Now, this might look a little funky to you, but it's just important to know that each of these, each part of this formula has a very real representation of of reality and nature, and so that surface integral of dA simply means the surface area of the Gaussian sphere that we just created. Okay, so think of it as a variable that we're just moving to the other side. So if we take a look at this here, we know that the Q enclosed is the total charge Q, okay, epsilon naught, and the surface area of this sphere would just be 4 pi r squared. Okay, and if you take a look here, we know that the epsilon naught and the 4 pi, this is, or 1 over that is k, and so what we get is kq over r squared, where r is any distance away. So from, let's say, from here to here, right, at this point here, we can say this is r distance away. And so this tells us the formula for the E field at a distance r away. And you'll notice that this is just simply the point, the charge point E field formula, where we discuss as E is kq over r squared. And the idea behind this is that the sphere itself isn't a point, right? It's not a charged point, it's an object. But if you go further and further and further away, the sphere eventually starts to look like a point. And so we can treat it like a point, especially in terms of the Gaussian sphere. All right, now what about the interior? So the interior, I'm going to draw the sphere, but a little bit bigger so that we can mark on the inside of the sphere. All right, so here we have our insulating sphere, and what we're going to do is we're going to create our Gaussian surfaces within the interior of the sphere. So I'm going to draw 2 of them. The first one is the smaller Gaussian surface, and we'll call this Gaussian surface 1. Okay, and the other one will just be on the outside of it, and it's going to be a full sphere away, but this is Gaussian sphere 2. Now, a couple of things to note, okay? This is a 3D shape, meaning that it's a sphere and not a circle. Okay, so keep that in mind. And so if we take a look at the formula here, E dot dA is equal to Q enclosed over epsilon naught. This is where the narrative of what the formula represents is very important. So if we take a look at the insulating sphere of Gaussian sphere 1 and Gaussian sphere 2, it's very important to realize a couple of things. So the amount of charge enclosed in 1 is less than the amount of charge enclosed in 2. Now, I keep on saying the word enclosed because if you remember, it's only what we are enclosing within the sphere that matters. Everything outside of the Gaussian sphere doesn't matter. And so therefore, we can say that the E field that's emanating around Gaussian sphere 1 is less than the E field emanating at Gaussian sphere number 2. All right. So if we take a look at the formula here, this is where things get a little bit different. But as long as you keep the narrative going and that you're able to describe everything, it's no real different than what we did before. So we're trying to find the E field, and this surface integral dA, that is still going to be the surface area of your Gaussian sphere. But what we have to change now is this idea of Q enclosed. This is now different because before, when we're outside of the sphere, our Q enclosed was the actual amount of charge. But because we are within the sphere, we don't have the same total amount. And so what we get here is a ratio. So if Q total divided by the volume, okay, and we use the volume because it's a sphere, okay, is equivalent, okay, ratio-wise of the charged enclosed and the Gaussian sphere volume, okay. So this ratio here has to be the same here, and we do get this a variable, and this variable is rho, and this is a charge density, right? It's charge density, but this is for volume. And there's different ones for area, and I forgot the other one. There's charge volume, charge area, and I think like a line of charge. Okay, but there is a different variable, but the idea is the same. It's your ratio, the amount of charge per whatever unit of dimension that you're looking at. In this case, this unit of dimension is volume. Okay, so knowing this, right, if I were to write this as just like Q total over volume total, so the volume total would be the total volume of the sphere. So it'd be 4/3 pi capital R cubed, where capital R is the actual radius of the sphere itself. And so let's write that R is actual radius. Okay, and it's because lowercase r represents the radius of the Gaussian sphere, right? And so this will be Q enclosed over 4/3 pi r cubed is equal to rho. And the reason why this is important is because now what we did is we created a substitution, right? And so I'm going to rewrite this as Q enclosed is equal to Q total times the volume enclosed, or excuse me, the volume of the Gaussian sphere, which is the volume enclosed, right? So volume of the Gaussian sphere, all divided by volume total, right? And I wrote it like this, but you can rewrite it like this, all right? And so there's like very cool things that happen when you write it out with the substitutions in place. Okay, what we see is that we get Q total times the volume of the Gaussian sphere, which is 4/3 pi lowercase r cubed, all divided by 4/3 pi uppercase r cubed. Right? We have a lot of things that cancel out. This 4/3 cancels out, this pi cancels out, and what we're left with is Q total. Q total r cubed divided by capital R cubed, and this is your charge enclosed. Okay, all right. So if we go back to this Gaussian surface formula, now we could rewrite this as E is equal to Q enclosed over epsilon naught times the surface integral dA, right? And if we put in our substitution, what we get is Q total divided by, let's see, Q total R cubed lowercase divided by capital R cubed, right? So this is all Q enclosed times 1 over epsilon naught, and the surface integral is the surface integral of the Gaussian surface area, which is 4 pi lowercase r squared, right? And algebraically, once again, cool things happen. This cube goes away because there's a square down there, and we're left with Q total divided by epsilon naught, so 4 pi epsilon naught r cubed times r. And what should I do? Oops. I'm going to put all this out here in parentheses, simply because in the scope of this problem, everything that you see in that parentheses is considered to be a constant. So the relationship between E field and the radius is directly proportional. And so if we were to graph graph the relationship, okay, also up here what we see is that the relationship is a inverse square proportion up there of a sphere of e to r. We would say right there, this is where r is equal to capital R, where capital R is the actual radius of the sphere. We will get a linear line because it's directly proportional, and then we get 1 over r squared, like so. And that, my friends, is a relationship between E field and the radius of the Gaussian sphere for a insulator. See you next time. Bye-bye.